Hi, welcome back to our next session. This new section will be about the limit. We had discussed about the increasing, decreasing interval, concavities interval, the minimum, maximum, especially the relative extrema, also the points of inflection. That will help us to understand the shape of the curve, of the original function, and as well as the endpoint behavior that we will see the limit. We have seen the limit actually in our first chapter we discussed, which is chapter 2. And then in our chapter here, we will discuss something else as the limit as infinity. And that was the section about. That's the section. So first of all, we consider whatever we know, Consider then behavior. The function is 3x squared over x squared plus 1. That we can see, well, we have a function, we have a curve. That it's at 0, but we have the horizontal asymptote at x equals 3. Something like that. Something like that is the function of 3x squared over x squared plus 1. What we consider is, well, as the limit of x approaches to negative infinity of this function, we have the y value is 3. And the limit of x approaches to positive infinity of f of x, that is also 3. And well, from the knowledge or from what we have seen from our precalculus, that the power are same or the leading term are same for the numerator and denominator, the rational function will have a horizontal asymptote at the ratio of the coefficient of leading term, that we have 3's. And the curve actually showed us that, well, on the right to infinity and on the left to infinity, we have the asymptote at y equals 3. The 3 is the limit. So something related to the asymptote and end behavior. So for the horizontal asymptote, we have seen in precalculus, we just say, well, just memorize the leading term and the leading coefficient, the ratio will be horizontal asymptote if they are same. If top is smaller than the bottom, as for the leading term, then the horizontal asymptote will be 0. And also if top is bigger than the bottom, we will not have the horizontal asymptote. If one power more as the top than the bottom, then we'll have the slant asymptote. But something else is not covered. That's what we discussed before. So actually here, I'll give definition. The line y equals L is our horizontal asymptote. Of the graph of f when the limit from the left side goes to L, or it's from the right side is L. Right, not necessary to be both, but just one side has the L as infinity, as x approaches to either left or right infinity, then we get the line y equal L is our horizontal asymptote. Right, so of course, for the rational expression, we already know what that's supposed to be. So not necessary to evaluate the limit, of course, you already know. Like for function f of x equals maybe x plus 1 over 3x squared minus 5x plus 2. We have the horizontal asymptote already at y equals 0, since the top has leading term is first power, bottom have leading term to be second power. That's the horizontal asymptote is indeed y equals 0. But for some equation we're not pretty sure, like other type of like maybe exponential function. Or maybe given this type of function, we do not know what the horizontal asymptote will be looks like, right? Then if we're given that, we have to evaluate the limit from the left and from the right to see what will happen, right? What give us to be if the L exists or maybe infinity, right? If we have a certain L, then we have the horizontal asymptote, maybe at the left end or maybe at the right end. Right, so for some question which is not rational expression, then of course evaluating the limit will be a very good aid, right, to help us to find out. Well, still, we need to learn how to find out the limit as infinity. Anyway. Well, which if the r is positive integer and the c is a real number, then the limit as x approaches to infinity of c over x to the r is 0. Which means constant to any x to the positive integer power, right? That means anything we get infinity, constant over infinity will be a 0. And also goes to negative infinity, constant goes to that, is also a 0, since no matter what, positive or negative infinity, it approaches to 0 in either way, but that's a 0. For exponential function, that is because the nature of the graph how it looks like. When it goes to infinity, that does not exist the limit. When we have the negative infinity side of the exponential function e to the x, that we will get a 0 as the limit. Right? That is because of the nature of e to the x, how it looks like. Right, and that is could be extended to any base which is greater than 1, we have that property, which is less than 1, greater than 0, we have the opposite property. Right, the curve will be, if you remember, that will be opposite side. Right? So based on these properties, Well, based on these properties, we're able to do certain type of question. I would give the rational expression to the format of that over x to the certain positive power, then we can determine what we will have. And that's the technique how we do the infinity. Right, this question 5 minus 2 over x squared, right, which is, that is 2 over the square of infinity, right, if we break that down. But we know that already infinity squared is still infinity, constant over infinity, that is a 0. Right, and also if we have a question like that, we know that e to the x, as x approaches to infinity, is infinity, that we evaluate just directly. Three over infinity, which a constant divided by infinity is also set. The value is a 0. Right? Any constant divided by an infinity, no matter how large the constant is, right? That's still be 0 as we divide them. Right, that's one thing. As for those things, as for this question, we have the rational expression. If we evaluate, we know that approach to infinity has to be 2, right? But when we evaluate, actually use the term of infinity, what we can do with this type of question? Well, of course, if we directly input the infinity in, that we have a same degree of infinity over infinity, maybe different degree of them. But even though that infinity of infinity over infinity, we do not know, the result could be leading to a 0, could be leading to infinity, could leading to a random constant. Right? That's all the result it could goes. Like for example, if we have 3x squared plus 1 or x, that will yield to infinity. If we have this one, that will yield to 2. If we have 2 over x minus 1, that will yield to 0. Right? That's the knowledge as what we know from the pre-calculus as x approach to infinity. Right? Of course, the end behavior. That is, all of them are infinity over infinity. Yes, now it is infinity over infinity. That it can lead to 3 different results, which is called indeterminate form. Right, not only that, but anyhow, we'll have some other form, but the type infinity over infinity is one type of indeterminate form, which will give us, right, for this question, what we can deal with it is to divide by x for our numerator and denominator, what we can do is simplify the expression. Why do we divide by x is because x is the leading term or the greatest term in our numerator and denominator. What we could try to do is divide it by the leading term overall. So we get the numerator, that's 2x over x, 1 over x, x over x, and 1 over x. Well, we not evaluate the limit yet, so we keep that expression. We do division anyway. Oh, then this expression. 2x over x, that's 2, 1 over x remains, x over x is 1, 1 over x remains. Right? Then, now we can evaluate the limit. Right? As x goes to infinity, the term of constant over x to the certain positive power will go to 0. Two plus 0 over 1 minus 0, that's 2 over 1, which is a 2. So we always need to simplify the expression for the indeterminate form. The first form we see here is infinity over infinity. There the form could be 0 over 0, could be 0 times infinity. If you flip 1 to the denominator, that will be either 0 over 0 or infinity over infinity. Or if you flip those things up, that will give the term 0 times infinity form. Or the formats of 0 to the 0. Like the clear one was like x approaches to something, right? 0 to the 0 anyway. And infinity minus infinity is also the classic format. Or even another format we have seen was like 1 to the infinity, right? It's approaching to 1, but not close, but that to infinity is the form of indeterminate, right? We don't know what that is. So that, or of that maybe something is missing, are the indeterminate form that we need to be super careful about, be super careful, right, about what we'll do of them. Right, so let's see a couple more examples, then we'll move on to the next topic about what we can do with the indeterminate form. Well, actually, for rational function is an indeterminate form. If that occurs in that case, what we can do is divide by the leading term. Right? So as we have seen a couple examples, we'll see more. Limit as x approaches to infinity, 2x plus 5, 3x squared plus 1. Right, this now we know this thing we know that it's supposed to be 0. Right, so how it will be 0. Right? So the term is x, the term is x squared. So what we can do is divide it by either the x or divide by x squared. Either way will give us same thing. What I prefer to do is divide by the leading term over or. Right? You can try to divide by the leading term of numerator or divide by the leading term of denominator. Doesn't matter which way you do. Right? But personally, again, I prefer to divide by the leading term over or. Right? What we will have is 2x over x squared, 5 over x squared, 3x squared over x squared, and 1 over x squared. If you're familiar with this step, you can omit that. Then to just give the result after dividing everything. Then we get 2 over x, 5 over x squared, 3 plus 1 over x squared. Which we get this form. And we know that any constant over x to a positive integer power will be 0 at positive or negative infinity side. That we evaluate the limit, we get 0 plus the 0 over 3 plus 0. Simply it's just 0 plus 0 is a determinate form, which is still 0. No matter how you add 0, that's still 0. Right? Over 3, which is the result of 0. And the next question may be a little more trickier, You get what? 3x to the third plus 5 over 2x squared plus 1. Right, this is our next question. So, personally, I would like to divide it by x to the third. Well, what we can get is, well, the limit of x approaches to negative infinity of 3 plus 5 over x to the third over 2 over x plus 1 over x to the third. And then we approaches the infinity, right? 3 plus 0 over 0 plus the 0. But not that, right? This is not that accurate. We know that, well, that's negative infinity, but if you actually use your calculator, right, to find that result, constant over x to the third, if you use like 999 negative, use that to divide it, you'll get a very small but something negative 0. Well, it is a 0, but it's a negative number. Right, so they are zeros. Since we get odd powers, then we have all the zeros to be negative. That we get 3 over a negative 0, which is negative infinity. Right, so this one is maybe a little too hard, right? But it's understandable still. But maybe for questions in homework or in a test, that will be a little harder. But anyway, that's what it is. Well, the next question is about to find the horizontal asymptote of the function. One over 1 plus e to the negative x. Right, so as we seen before, based on the graph of our e to the x, right here is our graph of e to the negative x, that x approaches to infinity will be 0, x approaches to negative infinity will be infinity. Right, so based on those information, we find the horizontal asymptote. horizontal asymptote based on the x approach to infinity, what's the limit? X approach to negative infinity, what's the limit? Right, so what we do is first of all evaluate for x approaches to negative infinity of the f of x. Right, and we have seen the curve, right, together with the curve of e to the x, actually e to the negative x, that e to the negative x approaches to negative infinity, that is 1 over infinity. Which is 0. 1 plus infinity is still infinity, 1 over the infinity, that gives the value of 0. And when x approaches to positive infinity of this function, that is e to the negative x goes to 0 when it approaches to positive infinity. That is 1 over 1, which is 1. So we have the horizontal asymptote of f of x is y equals 0 and the y equals 1. If you want to make it clear, because as x goes to negative infinity, we get the horizontal asymptote at y equals 0. As x goes to infinity, we have y equals 1 as x approaches to infinity. Right? So that is clear that the right behavior we get the horizontal asymptote at 1. The left behavior we have the horizontal asymptote at x equals 0. Right? For the middle behavior, we will see how we wrap up together with whatever we have seen in the previous sections in this chapter. Right? But anyhow, we have horizontal asymptote at least is defined. This question looks a little strange, right? It is rational function, but a little more things to be care about, right? We have radical of x squared minus x, which if we double check our domain, it is taking value besides the 0 to 1. If it's less than 0 or if it's more than 1, the denominator is well defined. Right, so x approaches to negative infinity, of course, it is defined at there. And basically the leading term we have on the denominator is square root of x squared, which is just x. Right, so same as the numerator, what it is. So how we do this question? We need to use a fact. First of all, since they both are x, so we divided by x to do the question. That is limit x approaches to negative infinity, x over x divided by radical x squared minus x over x. Now we face a problem that x need to be taken into the radical. Some fact we need to see. Based on the absolute function of x is positive x, when x is positive it's negative x when x is negative, but absolute function is also could be extended to radical of x squared. Right? If we see that the radical x squared is absolute of x, which is x if x is positive is negative x when x is negative. Right, so we use the fact that given our x is negative in our case, we have related the x to the radical x squared. Right, the negative x, when x is negative, we have that radical x squared is negative x. If we want to take care of the x, that x is negative square root of x squared. Right, so that is the illustration of what we do with this x on the denominator. Right, this x on the denominator. Well, the numerator, that's x over x. Denominator is, well, radical x squared minus x divided by negative square root of x squared. Right? The x is negative square root of x squared. That it can be divided, since they both are square roots. Right, since they both are square roots, they can be converted into 1, and they still have the negative sign outside. That we get, after we dividing them, 1, negative square root of 1 minus 1 of x. For x to be negative infinity, this one to be a 0. Well, negative 0 doesn't matter what it is, but that's still a constant. Minus or subtract the 0, that's 1 over negative radical 1. That is 1 over negative 1, which is negative 1. Right, so we use the fact to help us if we're facing the radical question. And of course, in our question, it's nicely that we just have radical x squared as the leading term on the bottom, which is still the x. Right, then we use the fact we can divide by x for the top and bottom, and taking the x inside the radical to get its negative square root of x squared, since we get x is a negative number. Whatever it is, it approaches to negative infinity, but that is still negative. Right? So that's what it's supposed to be. Right. Then the next topic is called L'Hopital's rule. L'Hopital rule. If the limit of x approaches to c of f of x over g of x, right, rational expression, that's the numerator over denominator, is an indeterminate form. Is indeterminate. Right, if this is an indeterminate form, for example, we have infinity over infinity, 0 over 0, or some other type of indeterminate form are kind of more special, right? We need to do something else with them to fix the term into this form. Or some other indeterminate form, we maybe do some work into this or that format to a rational expression format. We'll see them later, how we deal with it. And f prime of x, g prime of x exists. So function of a function is indeterminate and the derivative of them exists. Then what we can do is the limit of x approaches to constant of f over g equals the limit of x approaches to constant f prime of x over g prime of x. Alright, this L'Hopital rule is can be moved forward. Right? It's just one step like that. If the original function is indeterminate, then f prime g prime exists. Then we can apply the derivative of each numerator and denominator. Then we get a new limit. Maybe doable, right? But if the new format is also an indeterminate, then we can apply the L'Hopital rule again, right? The derivative of new function of numerator and denominator will be the new limit, and that's equal to original, right? So that's first step, but if appropriate, then we could move on to the next and next and next step until the L'Hopital rule not apply, right? Which means until the function is able to determine what the value is. Right, so that is L'Hopital rule, and we just see the example. We're gonna see the example how we deal with the L'Hopital's rule. Example. Find the limit. Sin ax over sin bx, of course, a and b are real numbers, right? Just the scalar of x. Right, we have seen before that, well, the limit x approaches to 0 of sine of x over x equal to the 1. Right, that, well, this could be extended, that sine of ax over ax is also 1, which means the inside term and the inside term of sine is equivalent to the sine itself as the limit of x approaches to 0. Right? That's equivalent can be substituted. So as x approaches to 0, that's same as ax over bx, which is a over b. Right? That is one way we can approach it. But since we check the condition, right, if we do just regularly, right, we figure out that, well, this, if I put 0 in, that's sine of 0 over sine of 0, that is the format of 0 over 0 as indeterminate. Right, that we could write it above the equation sign. Then what we could do is apply the L'Hopital's rule. Well, we could apply the L'Hopital's rule. Still have the limit x approaches to 0, but the derivative of sine separately with the derivative of sine on the bottom, right? That's what the L'Hopital's rule say. Right after if you like familiar with what you need to do, you could omit a step. Right, then that will be approaches to 0 cosine ax multiplied by the derivative inside cosine bx times the derivative of inside is b. Right, then we evaluate the 0 again, which we get here as well cosine of 0 times a cosine of 0 times b, which is still the 0. That is 1 times a, 1 times b, which equals a over b. A over b. Right, so that is one type of the L'Hopital rule, how we can apply this. Right, next, we just seen how we apply the L'Hopital rule for the different type of questions. Right, so find the limit as x approaches to infinity of pi over 2 minus arctangent of x over 1 of x. Right, this one we evaluate infinity to that we get 1 over infinity, that we get pi over 2 minus arctangent of infinity is pi over 2. We'll get 0 over 0. Right, so that format is an indeterminate 0 over 0 format. Then we apply the L'Hopital's rule. To that, which is the limit x approaches to infinity of a derivative of top, that's negative 1 over 1 plus x squared. Derivative of x to the negative 1, that's negative 1 over x squared. If we simplify a little, that is x squared over 1 plus x squared. You could apply the L'Hopital's rule since that's infinity over infinity. You could divide it by x squared to make sure that, well, to see what it is. 1 over x squared plus 1. That you apply the infinity to, that's 1 over 0 plus 1, which is a 1. Right, so this format, we are, well, even though that's the indeterminate, we're able to apply the L'Hopital's rule to make the function doable, right? Otherwise, the usual simplification way, we are not able to find out how to deal with this type of question, right? So if the question itself changed to something like x times pi over 2 minus arctangent of x, that is the format of infinity times 0, which you can flip the x down to the expression. Right, so some format I mentioned before as the infinity over times 0, which we can deal with that and flip one simpler one to the denominator would leave us a fraction, then make the question doable in that case. Right?